In this video, we're going to consider the orthogonality of the cross product with regard to two vectors. So part A asks us to find all vectors v so that the vector 1, 2, 1 cross the vector with v is the vector 3, 1, negative 5. And then it asks us to explain why there is no vector v such that 1, 2, 1 crossed with v is 3, 1, positive 5. All right, so for for part A, let's call the vector v a, b, c. We basically have a system of equations to solve. We need to figure out what a, what b, and what c are. So set up the cross product ijk 1, 2, 1 a, b, c. Rewrite our cross product by expanding along the row with the ijk in it. When we do that, we get the determinant 2, 1 bc times the I minus the determinant 1, 1 ac times the j plus the determinant 1, 2 ab times the k. That must be equal to the vector 3i plus j minus 5k, converting the component form to the ijk form. Now let's take our determinant 2c minus b times I, c minus a times j, and there's a negative in front, and then b minus 2a times k. That still has to equal the vector 3i plus j minus 5k. Now we equate components and set up a system of equations. Just rewrote this one a little bit, writing them in alphabetical order essentially. We get minus b plus 2c, that has to equal 3. In the second one, if we distribute the minus sign through, we get a minus c has to be 1. And in the third one, we get negative 2a plus b has to be the negative 5. If we look at the first equation and the third equation, if we add those two together, notice that the b's will cancel each other out. So when we add those two equations together, we get the equation negative 2a plus 2c equals negative 2. Along with the equation a minus c equals 1. These two equations are actually equivalent to each other. If you were to multiply the first equation by 2 and add, you get 0 equals 0. Those two equations are giving you the same information. So we can choose c to be anything we want. Actually, we could choose a to be anything we wanted as well. But let's think about it as terms of choose c to be whatever we want. If I do that, then the a number has to be c plus 1. And if we choose the c to be anything we want here, then the b has to be 2c minus 3. So any vector of the form c plus 1, comma 2c minus 3, comma c, any vector in that form for any real number c will satisfy the equation. For part B, we note that if we take 1, 2, 1 and dot it with 3, 1, 5, this vector is not orthogonal to 3, 1, 5. Remember, the cross product is supposed to give you a vector that's orthogonal to each of the two vectors in the cross product. So notice in this original part here, if we take the 3, 1, negative 5, we get 3 times 1, 1 times 2 gives me 5 when I add those together, and then minus 5 will give me a 0. So this vector really is orthogonal to 1, 2, 1, and you can check that 3, 1, negative 5 is orthogonal to any vector of this form if you go through the dot product. However, if you take the vector 3, 1, 5 and dot it with 1, 2, 1, you don't get 0. You get 10. So 3, 1, 5 is not orthogonal to 1, 2, 1, so it certainly can't be the cross product of 1, 2, 1 with anything, because the cross product is supposed to be orthogonal to both of the things that you started with in the cross product.